Hi, and welcome to the first video for Chapter 8. You can find the lecture notes in the Week 7 module right here. Chapter 8 is about relating two continuous variables. So far we have focused on one variable at a time, like the mean weight of eggs. In this chapter, we relate two continuous variables to each other. Generally, those variables are called x and y, and x is the independent variable and y is the dependent variable. So let me just use an example. I'll use an example from homework. Let's see if I can use... Here we go. So statistics students in Oxnard College sampled 10 textbooks in the Condor bookstore, recorded the number of pages in each textbook at its cost. So we have a continuous variable, which is our x, and you can see it takes values between about 250 up to about 750. Technically, you couldn't have a book with a fractional page, but it's there's enough spread in this range that we would consider this continuous. And then over here on the right, we have the cost of the books in dollars and cents. So these are two continuous variables, and we want to understand the relationship between them. There's two main ways to do that. The first, well, before I get into that, let's remember that we have the spectrum for understanding data. We have the raw data, which we see here. And let's see if I can copy this in. Go. So there's our raw data. It gives us all the detail, but it's pretty hard to understand the relationship. I might look at this 251 and notice it's got a pretty small cost of $41, and the 753 seems to have a bigger cost of $108. But understanding that relationship can be pretty challenging. So we can think about understanding data using visuals, and the most common way to understand data using continuous variables using visuals is with a scatter plot. So I'm going to take a minute and move this data into R and show you how to make a scatter plot in R. All right, I went and put the data into R. There are two vectors of data, so I use the C notation with comma between the points. And I can look at X and I can look at Y. We're going to make a scatter plot to explore the relationship between X and Y visually. And the code is very simple. You just say plot X, Y. And when you run it, it creates a graph that has the X value on the X-axis and the Y value on the Y-axis, and puts a dot where each of the data points are located. So I don't know about you, but I can immediately see that there is a relationship. Let's call it a mathematical relationship between the variables. So I'll drop this code into the lecture notes. And copy that graph. Okay, I didn't title the scatter plot. I was moving quickly, but it's a good idea to say scatter plot between number of pages in a book and cost of the book. And with this scatter plot, I can immediately see that longer books tend to have higher prices. That's the type of relationship we're talking about between two continuous variables. When the x variable is larger, the y variable also tends to be larger. The x variable, which is number of pages, is my independent variable because when we think about books, normally the length of the book is determined by the author and the price of the book comes later, as opposed to someone saying, hey, I want to write a book that I can charge $200 for. How long should that book be? Nobody really writes books that way. They sit down, they write a book, and they're like, whew, that book's 150 pages. I think I'm going to charge this price for it. Also from the visual, I can tell that the shortest book is under 300 pages and costs just over $40. The longest book is over 700 pages and costs around $110. So we can pull out a good amount of information. I can see that the mathematical relationship is pretty strong because all except one of these points lie very close to a line that slopes up from the leftmost point to the rightmost point. If you were to draw a line in here, a lot of these books lie very close to that line. There is this one here that's 500 pages and only costs $65. I can also see that there is at least one book that doesn't fit super well with this trend. So we can pull a lot of information out of a visual representation comparing two continuous variables. The scatter plot, for the most part, is the only visual you'll need to compare two continuous variables. There are some other ones, but I'm not going to get into those. So now let's look at summary statistics. There is a summary statistic for understanding the relationship between two continuous variables. It is called the correlation or the correlation coefficient. It is a single number that describes how closely those points lie along a line and whether that line slopes up or down. That's one way to describe it. Another definition is a correlation coefficient describes the strength of the relationship between two variables. The letter used for correlation coefficient is the letter R, but I will generally type out correlation coefficient or at least correlation. Correlation is the correlation between two variables can take any value between -1, and +1. A correlation coefficient equal to -1, well, I'll start with 1, equals to +1 means that the variables are positively correlated and the correlation is perfect. Knowing the independent variable can tell you exactly what the dependent variable is. It is in statistics, you will never see a correlation equal to 1 because things don't happen perfectly in statistics. But the closer the correlation coefficient is to 1, the stronger the positive relationship between the variables. And the closer the correlation coefficient is to -1, the stronger the negative correlation between the variables. So what would a negative correlation look like? A negative correlation could be between the intensity of the sun and the length of time to a sunburn. The stronger or the more intense the sunlight, the less time it will take to get a sunburn. All right, so as X goes up, Y goes down. Finally, a correlation close to 0 means there is no relationship between the variables. Knowing what X is tells you nothing about what Y could be. So that's our summary statistic, the correlation coefficient. It's very easy to do a correlation coefficient in R. There are really two different ways to do it. The simplest code is core XY, but I recommend you use core.test because this is going to give us a little bit more information. So let's use core.test. And it looks at the data X and Y, and it gives you the correlation right here. So the correlation coefficient is 0.963. This is extremely high. There is a very strong relationship between X and Y, and it is positive. Correlation test also tells you some other things. It tells you the p-value. So the p-value of a correlation test is basically tells you if you should accept that there is a significant relationship between the variables. A small p-value, let's say less than 0.05, is usually required to conclude that the relationship is significant. I'm going to show you a couple different data sets where they have positive, negative, and 0 correlation coefficients. So first, let's look at one that has a positive, strong positive correlation. Okay, so here's my X and Y. And let's take a look at it, just X and Y by themselves. All right, so there's our raw data. Definitely has information, but certainly hard to interpret the relationship between the variables. So let's scatter plot these. And we see a very, very, very strong positive correlation coefficient because they sure look like they're all lying on the same lines. I built that way on purpose. And let's find the correlation coefficient. We get a 0.98, 0.99 actually, which is super small. The p-value is 2.2 times 10 to the negative 16, or approximately 0, which is saying the interpretation of that is if this were data randomly selected from two different variables, X and Y, the likelihood of seeing this correlation, if they were not in fact very strongly related, is essentially 0. So we conclude that they are in fact strongly related. All right, let's do another one. We'll keep the same X, but now Y is going to be different. Let's see. I'm going to do a little bit of work here, and that shouldn't be too hard to come up with something. Okay, so let's look at, let's plot. Let's plot those. And there we have our data. Now, immediately look at this, and I say, this is not as strongly correlated as the previous data sets. The dots are spread out more around the line that I could imagine. However, it is clear that in general, larger X values are tend to be matched with smaller Y values. So the correlation, while not super strong, is negative. Let's take a look. Core.test XY. And we get, a negative correlation equals negative 0.41. That's negative, first of all, and it's not super close to -1. So a negative, but not super strong correlation. However, the p-value is still small, is about 0.00000219. That's too many zeros. It's still super small, so this correlation is significant. Now, that's something to keep in mind. A strong correlation or weak correlation doesn't mean it's not a significant correlation. So those are slightly different ideas. All right, now let's look at two variables that are probably completely, it's going to be a little bit random. Uh, completely randomly related to each other so that there is no correlation or very close to zero correlation. So I'll use the same X. But a different Y. Let's look at the scatter plot. And it's just kind of a big blob of data. There is no obvious upward or downward trend to the data. And if I were to put a line through that data, I could really put it anywhere and the data wouldn't match super great no matter what. So I'm going to say this looks like there is zero correlation or close to zero. Let's take a look. Sure enough, we have a correlation is 0.13, which is pretty close to zero. But even more importantly, the p-value is 0.2073. This means that if these two variables are not related at all, I could still end up with this data set, a data set that gives me this correlation, end up with a sample with this correlation 20% of the time, which is not strong evidence that these variables are correlated. So the p-value leads us to conclude that the data is the two data sets are not correlated. In fact, we can't say that they are. We fail to reject the idea that they are. All right, I'm going to pause the video while I copy all of this into the notes, and then I'll wrap up with this video, and then we'll do the last video. All right, so that covers the main summary statistic for understanding two continuous variables. In the last video, we'll go a step farther and we'll say, what if I wanted to use the independent variable to predict the dependent variable? And could I use some kind of line to give me a best possible prediction? I'll see you at that video.